And we're back at it. This is lesson 6 in Math 221 at SUNY Geneseo. On today's show, we talk about this thing called continuity. Continuity is an interesting idea because we don't normally think of continuity. We normally think about discontinuity, and we will certainly do that throughout this video. There are a few things that we think about when we think about discontinuities. I will draw pictures of 3 of them because sure and of course. There's this scenario that we think about when we think about discontinuity. There's a hole in the function, dear Liza, dear Liza. We think about this situation also when we think about continuity. There is a break in the action over there. And then we think about this scenario when we think about continuity. In each of those cases, there's a break in the function. So when we think about continuity, we're thinking about being able to draw the function smoothly, maybe, doesn't matter if it's smooth, but we're talking about drawing a function without picking our pencil up from the paper. If we can draw the function without picking our pencil up from the paper, we say that the function is continuous. But this is a break in a function. This is a break in a function. This is definitely a break in a function. So it's hard to talk about continuity without thinking about discontinuities. Your author Strang and his friend Herman give this a try. Here's what we mean when we talk about a function being continuous at a point, and this is screenshotted right out of your textbook. So we say that a function is continuous at a point A if and only if the following 3 conditions are satisfied. First, the function has to be defined at A. There has to be a point whose x-coordinate is A. Then there has to be a limit as x approaches A from both directions. They have to match. And then the limit has to be the function value. If those 3 things all happen, then we have continuity. If a function fails to be continuous at A, we say that it is discontinuous at A. So consider the following. Consider f of x, which will be the function x squared minus 5x plus 6 over x minus 2 at x equals 2. If you were to graph this function, it looks like so. That's the x value 2. That's the y value 5, and you'll notice that the function never gets to 5. It tries all the other y values and then skips right over 5. So this function is discontinuous at x equals 2. Why? Because there is no value for f of 2. If you try to figure out what f of 2 is, you get 0 in the numerator, 0 in the denominator. That is an undefined situation. So this function has one discontinuity, and that's at x equals 2. Consider g of x, where g of x is a piecewise defined function. It's negative x squared plus 4 if x is less than 2, and it's 3x minus 1 if x is greater than or equal to 2. And so this scenario plays out like so. As x approaches 2, so we notice that g of 2 is defined. G of 2 is this number 5. So g of 2 does equal 5, but the limit of g of x as x approaches 2 does not exist. Why does that limit not exist? Because the limit of g of x as x approaches 2 from the left is 0, but the limit as x approaches 2 from the right of g of x is 5. So if the limit of g of x as x approaches 2 from the right is different than the limit of g of x as x approaches 2 from the left, we say that the limit of g of x as x approaches 2 does not exist, because those limits from the left and the right have to be the same. So something for you to think about on your own: determine the value of b that makes h of x continuous, where h of x is this piecewise defined function. It's x squared plus b if x is less than 1, and it's 2x plus 5 if x is greater than or equal to 1. So you imagine this is a parabola and this is a line, and we want them to match up at the x equals 1 place. That's something that we'll talk about when we gather. You should have an answer at the ready. Some things to consider. Polynomials are continuous at every real number. And why is that true? Well, you think about what a polynomial is. A polynomial is something like x cubed plus x squared minus 2x plus 2018, or whatever it is. So to be continuous, there has to be a function value, and clearly any real number can go in there and you're fine. But then the limits have to exist as you approach any number that you choose. And we know that the limit of a number is fine, and we know that the limit of x is fine. Those are fine. So then what? Well, this is a number times itself, and limit laws say that those limits just multiply. Those limits just multiply, those limits just multiply, and then we're adding limits together, subtracting limits. Those are all legitimate. So by limit laws, this function is going to be continuous everywhere because the limit is going to match the function value everywhere. In fact, it's not just true for polynomials. Rational functions are continuous on their domains. Well, why is that true? Well, that's true because what's a rational function? A rational function is some polynomial over some other polynomial. And we know that quotients of continuous functions are fine because the limit laws give us that the limits will divide as long as this function is not 0. But it's okay, if this function is 0, then that's not part of the domain in the first place, so we're fine there. And then, just to set your mind at ease, trig functions are continuous on their domains. And that's something where the text has a nice proof of why that's true. Sine and cosine are both continuous. You can prove that sine and cosine are both continuous at any point in their domain. And then every other trig function comes from sine and cosine. So once you have them, you have everything. That is on page 196 in the PDF of your text. It is worth a look. So if those are all continuous, well, let's go back and revisit the things that are not continuous. Let's go back and revisit those if we can. So what are the three kinds of discontinuities? Well, over here in red, this is a point discontinuity. And a point discontinuity happens wherever f of a is just, it doesn't exist. So here's a, There is no value f of a, so we don't have continuity, because to have continuity we have to have all of these things, and that doesn't fly. In green, we have what we call a jump discontinuity. In a jump discontinuity, the limit of f of x as x approaches a does not exist. There's a, and there's no limit for the function as x approaches a. So you need this to happen, and it doesn't. That's the same case here. It is also this scenario. This is sometimes referred to as an infinite discontinuity, a case where the limit as x approaches a from either the right or the left is one of the infinities, either positive infinity or negative infinity. So we're clear with nomenclature. This kind of discontinuity is sometimes referred to as removable, because if we were to plug in that hole right there, we would have a continuous function. These two are sometimes referred to as non-removable, because there's no way I can bring those two pieces together. There's no way I can avoid the fact that this goes infinitely large. So those are sometimes referred to as non-removable. All right, so you should have some things to think about, and I will give you some things to think about. Out of section 2.4, you probably want to consider questions 138 and 139 and 145 and 147. Those are some questions worth considering, and we will gather in class soon.